Hello. Today, let us see how we can use what we learned about the ellipse to construct a hyperbola. First, let's start with the definition. A hyperbola is a plane curve where, for any point on it, the difference between its distance to one focus and its distance to the other focus is constant and equal to 2a, where a is the length of the semi-major axis. How can we use the parametric tab with geometric and dimensional constraints to represent this curve? Just like with the ellipse and the parabola, when I move these two lines, a set of points is formed. But we need to check if they actually satisfy the condition from the hyperbola's definition. How do we make sure the condition is met? First, we place the two foci. Then, from one focus we draw a circle, in this case with radius 140 millimeters. This represents the larger axis. Just as with the ellipse, the hyperbola also has a major axis. Here the value of semi-axis A is dimensioned as 70. Next, at the midpoint between the foci, we draw another circle whose diameter equals the distance between the foci. When we draw this circle, the intersections at 70 millimeters left and right give us 4 points that form a rectangle. From this rectangle we get two lines, which are the asymptotes of the hyperbola. And indeed, when we start stretching the hyperbola, you can see that the curve approaches the asymptotes but never touches them. So how is this construction achieved? The first line must be fixed at one focus. The second line is connected to the first, and always directed toward the other focus, using the coincident constraint. These two lines must always remain the same length. The reason is that the difference in distance between the point and this focus and the distance between the point and another focus is this distance. And that is the circle radius of 140 millimeters or 2a. This is the condition that guarantees we are constructing a hyperbola. Now, just like with the parabola, we need characteristic points for drawing the spline. Again, we'll use the spline command with control vertices. We need 3 control points. How do we find them? I won't go into the math here. You can check out our blog for the detailed calculations, but I'll give you the results. On this line, which is 2a units away from the center. As you can see in properties, it is 140 along the x-axis. We need to place 2 points. Using the point command, I'll place one approximately here on the vertices layer. Its x-coordinate is 140, and the y-coordinate is calculated as b times the square root of 3, where b is the minor semi-axis. With the calculator we compute the exact value, apply it, and place the point. Then we mirror it for symmetry. We add one more control point. Its y-coordinate is 0, and its x-coordinate is 35, which is 1/2 of a. Connecting these three control points with a spline, however, gives us a parabola, not a hyperbola. What do we need to do? We change the weight parameter to 2, and now we have a hyperbola. Zooming in, you can see that as we move the point, it perfectly follows the hyperbola line. Now, what if we want to extend the branches of the hyperbola? We will create the hyperbola from here. The process is the same. We need 3 points, 2 of them symmetric. One is here, another here. For this point, the y-coordinate is 0, and the x-coordinate is 17.5, which is a divided by 4. Why exactly a divided by 4? Because this line is at a distance of 4a. 70 times 4 equals 280. For this point, the x-coordinate is 280, and the y-coordinate is calculated as b times square root of 15. Using the calculator again, we compute and place the point. The math used behind will be explained in our blog linked below. But, just 15 is 4 squared minus 1. In the same way, the square root of 3 used for the previous hyperbola was calculated as 2 squared minus 1. Here the distance was 2a. And here it is 4a. We click Apply, and the point is placed. Then we mirror this point. And finally, we connect the points with a spline. The line we got is a parabola. To get a hyperbola, we adjust the weight of the second control point to 4. You might notice the new hyperbola doesn't align perfectly with the first. Why is that? First, let's zoom in on our new hyperbola. It doesn't look as symmetrical as this one. It seems shifted upwards. I'll select it again. Take a look at what it says here. Data points, number of control points. 4. For these constructions with ellipse, parabola, and hyperbola, the spline must always have 3 control points. And the degree of the polynomial curve must be 2. The mistake was likely caused by overlapping points. Repeating the spline command correctly, selecting 3 control points and confirming with Enter, gives us the right shape. The number of control points is 3. The polynomial degree is 2. When we set the weight of the second control point to 4, both hyperbolas match perfectly. Math makes it possible, AutoCAD makes it visible.